Hi everybody, like Mackenzie said, my name is Jared Malvolti, and my company name is Innovation of the Future. So, one day, I was talking to my brother on the phone, and he presented a problem to me. He told me that he owns a smaller dog, her name is Gracie, and he was telling me that each day he feeds his dog, Gracie, 1 cup of food. And on some days, Gracie does not eat all the food, whereas on other days, Gracie does. So on those days that Gracie doesn't eat all the food in her bowl, my brother Josh, he will usually throw an extra cup of food in the bowl just to be safe, to make sure his dog is fed for the day. He has told me that he is pretty sure that he has thrown extra food in on some days, and so this caught my curiosity that he was overfeeding his dog, so I decided to research the topic a little bit. So, I found that this is a widespread problem. According to ASPCA, a non-for-profit animal rights association, they say as a responsible dog owner, one of the most common pitfalls you have to watch out for is overfeeding. The same source says that dogs will not stop eating when they are full, and this is backed up by CNN saying that over 41 million dogs are overweight throughout the world. So, I want to create a solution to this problem. So my goal is to create a food bowl that feeds the dog the right amount of food at the correct time of day. And then in cases where, my brother's situation, where the dog does not eat all the food in his bowl, it replenishes that food to the correct amount that's supposed to be the next day. So there are some previous solutions out on the market today. I broke these solutions up into 3 different types. The first type is a motor-driven dog food dispenser. This one, the food starts in a hopper, which is a storage compartment, and a motor drives the food down a chute and into the bowl. Reading reviews and how it works, it dispenses in increments of half a cup, 1 cup, etc., based on how many rotations the motor turns to dispense. The middle solution, the gravity flow solution. So the food starts in the hopper, and the force of gravity makes the food go down the chute and into the bowl, and it keeps the food bowl full continuously. And the third solution is what I like to call the storage container feeder. With this solution, you are able to preset meals for your pet, either 2 or 3 or more in advance, and then set a timer to open up the compartment and allow your pet to eat. These are the different patents for those current solutions. The patents are below there. So based off of user reviews on online sales websites, my own ideas, and a little bit of input from my brother, I came up with the criteria I wish to satisfy through my solution. The first one is cost. I want to be able to produce this solution for $40 or less. That way the resale price is right around or below the current solutions out there. I want it to be effective, so I want to feed the pet at the right time of day, the correct amount, and then be able to know how much food's in the bowl at all times. The third one is storage capacity. I want to have a large supply of food in the hopper, because if you were to refill the hopper every day, that would just defeat the purpose of having an automatic dog food dispensing system. I want it to be low maintenance, so that the average Joe can take it right out of the box, read the manual, and set it up without interfering with it every day. And then I want it to be pet-proof, so the dog cannot reach up inside and access food when they're not supposed to. So I went through a brainstorming activity. I came up with 4 different ideas. My first one is a storage compartment. It has 4 different compartments, and you're able to preset 4 meals for your pet. And then on the front, it has a digital timer that you set for when you want to feed your pet. The second one is a smart dog food bowl, and it senses how much food's in the bowl at all times, and then you set how often you want to feed the bowl. And using these 2 variables, it sends a message to the owner when the food bowl needs to be replenished, either by text message or email. The third solution is a motor-driven dog food dispensing device. The major difference of this design and those out on the market currently is that underneath of the food bowl, it has a weight sensor that keeps track of how much food is in the bowl at all times. It then uses weight to dispense to know how much food to dispense, and then if there's food left in the bowl, it takes into account the food in the bowl, the food that's supposed to be in the bowl, takes those 2 variables, and figures out how much to dispense to the correct amount. And then the fourth one is a gravity flow dispensing unit. The difference with this one is it has a switch on the side, and the dog, you have to train your dog, the dog will hit the switch when it needs food, but so the dog doesn't continually hit the switch, so it has constant flow of food. It'll be similar to morphine pumps at the hospital, so it has a limit of how many times the dog can hit the switch in a certain amount of time. So I put those 4 ideas into a decision matrix, and based off my criteria, the one that fits my criteria the most is the third design, which is a motor-driven dog food dispensing device that has a weight sensor underneath of the food bowl. These are updated specifications on my device. So if you see here, the food starts in a hopper. And then a conveyor belt that runs to the back of the hopper drives the food out to the chute. The reason I have a conveyor belt running all the way to the back instead of just a wheel right there turning to push the food out is so that it pushes the food out while at the same time churns the food so that the food does not get jammed in the hopper on its way to the chute. That chute, if you look here, has an angle to it, kind of like an S-shaped curve. The reason I did this is so it's pet-proof, so the pet can't reach up in compared to if I would have put the conveyor belt running this way and the chute just going straight out. It's harder to reach up and in than just reaching in. And then the food bowl will be free from the system so that the owner can use their own food bowl for the system, because everyone has their own favorite food bowl. And underneath the food bowl will be the weight sensor. So I made all of my parts in Creo Parametric, which is a 3D design software. I'll start you off with the conveyor belt setup over here. I wanted to have a 4-inch wide conveyor belt, but based off of materials available to me, I could only find 2-inch width conveyor belts. So I ran 2 simultaneously right next to each other. So I have 2 side plates that hold the conveyor belt assembly in, and a center separator that separates the food into either conveyor belt. And then I have rollers running all the way back. That adds support in the middle, because if you had a roller on one side and a roller on the other side, you're going to have tension, or you're not going to have as much tension in the middle, so food can come down and add weight to that conveyor belt where it won't dispense as well. And those rollers add support. And then that entire conveyor belt assembly fits in the top part of my case over here. To give you some relativity, that's the front of the conveyor belt and that's the front of the case right there. And then over here is where the motor attaches to the system. Up here is an adapter where the hopper attaches to the case. The hopper I used was just a plastic storage container with a threaded cap, and that screws into the system right there, to the adapter right there. And then down here, I used a hinged door with springs underneath to calculate, with a linear potentiometer on the back to calculate the force going down on the door. I'll get back to the linear potentiometer later and explain more about how that works. So these are all the parts that went into this system. Going from left to right here, I've got the case, the adapter that transfers the hopper to the case, a lever to drive the conveyor belt. That was for early testing before I actually integrated the motor. And then the side plates that hold the conveyor belt assembly into place, and the center plate that separates the food into either conveyor belt. Then down here, you have the base. The base attaches underneath of the body, and then you see the hinges there for the hinged door. 2 side plates for the body, and then rollers for the support of the conveyor belt, a drive axle. My initial plans were to have a conveyor belt with gears on it. That's why you see the grooved edges right there. If you can see right here, that black strip has gears all the way around, and this is actually a food-grade conveyor belt that I was planning on using. But I designed my conveyor belt assembly in a perfect world, and when I tried to actually assemble it, it didn't fit. So I came up with a solution for that. I just used rubber bands running right next to each other, and that worked just as great as a solid conveyor belt did. Next part is a tensioner. That attaches to a spring on the side plates of the conveyor belt assembly, and that is to make the conveyor belt more tense or less tense, depending on how you need it. The motor clamp, you put the motor, it's a cylindrical motor with an axle that comes out the side. It clamps with those 2 screw holes at the bottom, and then it attaches that arm to the body. And then I need an adapter to connect the motor to the axle of the conveyor belt. So I designed an adapter. The diameter of the axle for the motor was 3 millimeters, and the diameter of the axle for the conveyor belt was 5 millimeters, so I had to come up with that adapter. That side's 3 millimeters, that side's 5 millimeters, and then those 2 holes right there are where set screws screw in and then clamp those axles and allows them to turn. So the materials I needed to electronically drive my prototype. Arduino board. Arduino boards are programmable boards. You write code and upload it to the board, and that's essentially the brain of the whole system. A linear potentiometer working as the weight sensor. So for those of you who do not know a linear potentiometer, it's this over here, and that slider bar right there slides left to right. When it's all the way left, the value is 0, and the farther it turns, or the farther it goes right, the higher the value goes. So it goes into the hundreds, 300s, etc. My next part was a 12-volt motor, which is shown right there, and then a relay. The reason I needed a relay was because the motor I used needs a 12-volt input to run, and the Arduino board only puts out 5 volts. So the relay takes the power from an external source and brings it into the system. So, these are pictures of my prototype. Actually, my prototype with me here today. So, if you look here, you can look inside and see my conveyor belt assembly. I have the rubber bands right there, and then the motor over here with motor clamp drives the food down this chute and then out onto a bowl that sits on top of that hinged sensor right there. And then it takes the reading. If you look, I'll direct you back to the PowerPoint. You see that little notch right there, that's the linear potentiometer, and that attaches to the end of the hinge door. And then these are just more pictures for those who couldn't see my actual prototype. Yeah, the conveyor belt assembly and the adapter. About the adapter. The adapter. I have the hopper here, and it screws nicely into the adapter. And then, if you look on top here, you see a little slit. That's designed for a piece to fit inside, seal off the hopper, so you're able to flip it upside down, put it on the system, and release all the food into the system. And my entire model was 3D printed. For you, of those in the audience who don't know what 3D printing is, that's the 3D printer I printed on over there. So 3D printing in plastic, it takes filament. Filament's essentially weed whacker line. It looks the same. It's just a thin line of plastic, and that thin line of plastic is fed up through a tube up into this extruder right there. And in the extruder there's a heated element. It heats the plastic where it's melted, and then it pushes that plastic out, similar to a hot glue gun. And it is on a 3-axis, X, Y, and Z. And it essentially goes down, draws lines right next to each other. It goes up a layer, and each layer is about half a millimeter. And it does it again, and it just essentially keeps building up that object. How is this a useful tool? Well, I was able to actually see what works and what didn't work, especially for the conveyor belt assembly. It is very different from seeing an idea on paper and then integrating it into an actual object. And then I'll actually have a demonstration prepared for my unit. So I'm going to fill the hopper up. this time, but this is just the first prototype. Let's start off with a clean bowl. And then I will start the program for you guys. And now this program is going to take the weight into account, and when it senses the food bowl, the food bowl is full, it's going to stop dispensing. Alright, and I'll show you guys that this just wasn't timed. When I lift the food bowl, it's going to start dispensing. Hopefully. Pressure plate got stuck, so I'll lift the pressure plate. And start dispensing, we put it back down, and it stops. That was a video just in case that didn't work. So I ran 3 different tests on that prototype. The first one was a dispense test. I used that lever I talked about earlier to simulate this first test. It was a pass or fail test to see if the system would actually dispense. So I went one rotation of the lever and ran it 20 times, and I looked and observed to see if the food only dispensed when the lever is being turned and stopped when the lever stopped. I ran that test 20 times. Out of all 20 times, it passed. So that system dispense rate has 100%. The second test was an amount test. Again, I used the lever for this test. So I turned the lever 1 rotation and then counted how many dog food morsels dispensed into the bowl. And I took those dog food morsels and changed that into a weight. So I ran 10 tests on this one. The average was about 97 of those dog food pieces per rotation, or about 2 ounces per rotation. And then my third test was an electronics and program test, which is essentially what I just showed you there with that simulation. And I tested it 10 times. Out of 10 times, it worked 9 times. And that 10% of the time that it didn't work, I researched a little bit, and I saw that was a result of a wire shorting itself out, a little loose wire, and shorted the circuit out, and the Arduino board wasn't getting a correct value from the linear potentiometer. So some experts I consulted throughout this entire design and development process. Joshua Malvolti, my older brother, he works at Caterpillar, and that's just not his day job. He's actually a founding member of River City Labs. River City Labs is a local makerspace here in the area. They're not-for-profit, and they have a workshop and people with the knowledge to help people like me accomplish personal projects, and they're very involved in the community. But they let me use machinery like a lathe to work on some of the parts for the conveyor belt assembly. They also gave me advice for that whole assembly, and then I ultimately had access to 3D printers through them as well. Reflecting back on my solution, some cons that could come up with my solution is that it's a smaller unit, so it can easily be knocked over by larger dogs. The solution for that one is make it heavier, so use heavier material or make the base larger, so it has a larger surface area with the ground, thus making it harder to turn over. The second con is that dogs can interfere with the program. So we've all heard of Pavlov. If you ring a bell while you're feeding a dog and run that test over and over, it gets to a point where if you just ring that bell without feeding the dog associates that ring of the bell with being fed, so it starts to salivate. So just like this, it's going to associate the sound of the motor turning and dispensing the food into the bowl with getting fed. The dog might get excited and push its nose into the bowl while it's dispensing and shut off the whole dispensing cycle. So my solution for that one would be to pre-weigh the food before it falls into the bowl. So up here, have it pre-weigh up here and then dispense the correct amount into the bowl. And then this solution isn't just for dogs. I use dogs in my main subject for my presentation, but it can be used for cats and other house animals. And I'd like to thank you guys for being such a great audience. Any questions?
All right. Have you tried it for different size of dog food or animal?
I have not tried to run that test on it. I thought about running like peanut M&Ms through it though.
That was one of my questions. considering the users of this, obviously, a Saint Bernard is gonna eat a lot more than a Chihuahua.
Mhm.
So is there accommodation for different, different appetites,
Obviously,
if you will?
a larger hopper, but that would also make it more top heavy, which would require a larger base as well.
So you may have to adapt it to the
Yeah.
dog that you own.
Mhm.
Same thing with the food,
Definitely, yeah.
size of the food
Mhm.
truck.
So, is the linear potentiometer your final solution?
It wasn't. I initially began with a weight sensor. It was supposed to sit underneath of the bait plate, but I couldn't figure out how to program that thing, so I went to a more simplistic programming of the linear potentiometer.
It's more wiring than programming.
Yeah.
So what happens when the dog spots the bull out of the way?
I didn't think of that one. I mean, I guess on the hinge door, you can make like a cutout of a bowl that fits in, so it wouldn't be able to move side to side. Like that lip underneath would fit into that cutout. That could be a solution for that.
Are you gonna go, did you intend to develop electronics to show the daily cycle? Or you said we dispense so much
I
and
didn't get
stop?
that far. I just dispensed, or I just showed you that it dispenses based off the weight. Yeah.
Does this fit within your $40 price target?
Well, I 3D printed my solution, and 3D printing is not the cheapest way to go.
Right.
I was definitely over $40 because this
Filament is
whole,
expensive.
this whole yellow part, the filament for that costs around $25 to $30. So
But if you produced it,
if I produced it, it would be like a plastic mold or a different material based on how heavy duty you'd want it.
so you think you'd be within $40?
I think I could be. I think I could make a couple.
Do you have the idea of getting the food manufacturers to sell plastic jugs full of dog foods? I don't even have to put it in.
That's a good idea. Yeah, that would definitely help boost sales of this and coincide with the sales of that.
Why?
Why
What would be the benefit
benefit what?
to the manufacturer?
Because it would make them the only ones that people would buy from.
Once you buy the device, so
You
you get the
wanna buy
device
the,
for free,
I wanna buy the
you'll
hopper.
razors and blades.
Oh, yeah.
Questions from behind us?
What was your biggest problem you had to overcome?
Biggest problem? Getting a successful print. If you look at my table, I have many failed prints.